Welcome to the early 1990s. Software engineering is a logistical nightmare, a sprawling, chaotic network of consumer electronics, desktops, and servers speaking completely different languages. The core limitation of the era came down to how software was built. If you wrote a program in C++, you had to compile your source code directly into the specific machine code of the exact hardware it was going to run on. This created massive operating system lock-in. A program compiled for a Windows machine was unreadable gibberish to a Mac or a Linux server. Developers had to write and maintain multiple distinct codebases just to reach a broad audience. In 1995, James Gosling and his team at Sun Microsystems released a new programming language designed to break this bottleneck: Java. The release was defined by a specific, ambitious slogan: write once, run anywhere. The mechanism to actually achieve this required an architectural shift. Java does not compile directly down to hardware-specific machine code. Instead, it compiles to an intermediate abstraction layer. That intermediate code is then executed by the Java Virtual Machine, or JVM. The JVM acts as a universal execution environment that translates the abstracted code on the fly for whatever host operating system it happens to be running on. Java achieved true portability by taking the burden of hardware translation completely off the software developer and shifting it onto the execution environment itself. To actually write and run Java software, you have to navigate a strictly nested ecosystem of packages. As we can see in this diagram, it starts at the top level with the Java Development Kit, or JDK. It is the master container that holds every tool and library required to interact with the Java ecosystem. Inside the JDK, you have tools meant strictly for the programmer. This includes the Java compiler, which converts your raw text into code, along with archivers and debuggers. Beside those development tools sits a distinct inner layer required exclusively for execution: the Java Runtime Environment, or JRE. It houses the standard class libraries and the Java Virtual Machine itself. The relationship is a strict formula: the Java Development Kit equals the Java Runtime Environment plus the development tools. This separation serves a practical purpose. Software developers need to install the massive, full-scale JDK to build applications, but end users, the people just trying to run those applications, only need to install the lightweight JRE. By tightly compartmentalizing these packages, Java ensures the execution environment remains completely isolated from the heavy overhead of the development tools. The lifecycle of a Java program begins when a developer runs their raw.java source code file through the JDK's Java compiler. The compiler processes the text and outputs Java bytecode. This is a standardized platform-independent instruction set saved as a file with a .class extension. At this stage, the bytecode is unreadable by a standard computer CPU. If you try to hand a .class file directly to Windows, Mac, or Linux, the operating system won't know what to do with it. To execute the code, the .class file must enter the JRE's runtime pipeline. As detailed in this flowchart, the first step is the class loader, which dynamically brings the files into memory. To optimize efficiency, the JRE does not load everything at once. The class loader only pulls classes into memory at the exact moment the program asks for them. Once loaded, the code hits a rigorous security checkpoint, the bytecode verifier. It scans the bytecode to ensure it doesn't violate system integrity, blocking stack overflows and illegal memory access. If the code is corrupted, the verifier halts the process.
Only after successfully passing these checks is the bytecode handed down to the interpreter. This strict JRE pipeline acts as an impenetrable buffer. It guarantees all code is structurally safe and perfectly formatted before ever touching the host hardware. Once verified, the code is fully inside the Java Virtual Machine. The JVM functions as a literal, abstract computer running inside your actual computer, complete with its own instruction set architecture and memory management system. Looking at the JVM diagram, the system partitions RAM into runtime data areas. First is the method area, storing structural blueprints like per-class structures, method data, and the constant pool. Next is the shared heap. Whenever Java creates a new object or array, it's dynamically allocated space here. Since objects take up significant space, developers use JVM flags to manually control exactly how much host RAM the heap can demand. While the heap is shared, JVM language stacks are strictly local. Each new thread gets its own isolated stack for immediate storage. It holds local variables, primitive data types, and execution frames to track method calls. Alongside the stack, the PC register tracks the exact memory address of the JVM instruction a thread is currently executing. Finally, native method stacks are reserved for when Java must interact directly with unrestricted C or C++ libraries. That rigid, strict syntax translates directly into this highly predictable memory architecture, creating exceptional, consistent stability at runtime. Let's focus on the bottom left of our JVM diagram. With memory allocated, the JVM hands the bytecode over to its final processing phase, the execution engine. The baseline method for executing this code is the interpreter. It reads the bytecode line by line and translates it into the native machine instructions required by the host hardware. The interpreter starts up immediately, but it has a massive flaw. Translating code sequentially, one single line at a time, creates severe performance drag over long, complex runtimes. To solve this bottleneck, the execution engine utilizes the just-in-time, or JIT, compiler. It monitors the interpreter, intercepting frequently repeated hot code. The JIT permanently compiles these chunks into native machine code, allowing the program to bypass the slow interpreter entirely. Meanwhile, a background process called the garbage collector constantly patrols the execution engine. Its job is to identify dead objects in the heap that are no longer being referenced and automatically reclaim their memory. To safely delete objects, the garbage collector occasionally requires stop the world pauses. The entire application briefly halts, ensuring memory is cleaned without data corruption. The execution engine generates high performance by balancing three forces: the fast interpreter startup, the optimized JIT compiler, and automated garbage collection. This diagram illustrates the rigid structure of a standard Java program, written specifically to prepare for this massive execution pipeline. Every application contains a main method class. This specific code block acts as the designated entry point for the JVM to begin its work. When executed, the text is fed into the JDK and compiled into Java bytecode. This bytecode is pulled into the JRE, checked by the verifier, allocated to stack and heap silos, and funneled through the JIT compiler to output a clean hardware signal. Write once, run anywhere is the result of a highly engineered, standardized pipeline taking on the burden of translation. Writing Java code is interfacing with a massive automated virtual machine, guaranteeing absolute hardware portability and memory security.